Hello. Today's topic is carry look ahead adder. Introduction to adders. What are binary adders? A binary adder is a digital circuit that performs addition of binary numbers. A binary adder takes two binary inputs, produces a sum and carry out. For example, a 4-bit binary adder takes two 4-bit inputs and produces a 4-bit sum and a carry out. Ripple carry adders. Ripple carry adder is a basic adder that processes bits sequentially. Uh, it works in a way in which there are two numbers. By connecting full adders in a chain, where the carry out from each full adder is the carry in for the next. The sum and carry bits are generated sequentially starting from the least significant bit. The RCA is slow because each adder stage can only produce its output after all earlier stages have produced theirs. The longest path in the circuit is through the carry lines. For example, an 8-bit RCA can take up to 8 nanoseconds to produce an accurate answer. The RCA is not preferred in many applications because of its high latency. A carry lookahead adder, on the other hand, is faster than the RCA because it calculates one or more than one carries before the sum. Why should we use carry lookahead adder? Why do we need faster adders? Modern processors handle large amount of data, 32 bits and 64-bit, etc., and operation need to be fast, especially in addition, as it's fundamental to many processes. Example for ALUs in CPUs and DSPs. Ripple carry adders limitations. It adds bits one by one, so its performance slows down for a larger bit width. The carry must ripple through all stages, which causes a delay proportional to the number of bits. The solution is carry lookahead adder, which reduces the delay by calculating carry in parallel rather than sequentially. Basic concepts of carry lookahead adder. The CLA uh, computes carry bits in parallel to avoid ripple delay. CLA predicts carry values for all bits in advance. There are two functions in the carry lookahead adder, which are the generate function and propagate function, where the generate function is the product of both AI and BI, which are the inputs, and propagate is the sum of AI and BI, which is or where in generate, if both the bits are 1, the GI value prevails, and in propagate, if one of the values are 1, or at least one of the values are 1, it prevails. Carry look at a formula is Ci plus 1 equal to Gi plus Pi into Ci. So Gi is the carry generated at the current stage, and Pi into Ci is the carry propagated from the previous stage. This formula allows calculation of each carry in parallel without waiting for the previous carry. Uh, all carries C1, C2, C3 up to Cn can be calculated in parallel using the formulas of G and P. The CLA block diagram, where C0 is the initial carry in, and A0 and B0 are the initial inputs, and S0 is the initial output, or the sum of A0, B0, and C0, where C0 is normally uh, 0, considered as 0, and C1 is the carry out of the sum S0, and this repeats until the answer is produced, or the value is produced. Timing analysis. In ripple carry adders, the timing is proportional to the number of bits, where if the number of bits is high, the uh, timing analysis also high. It is marked as O of n, where uh, Each bit must wait for the previous carry to propagate. So it's basically says that it's done sequentially. uh, the advantage of speed in CLA. Carry look ahead adder compute carry bits in parallel. The delay is reduced to O of log n, meaning the time to calculate carries is less. Uh, so this is the circuit diagram for CLA, where as you can see, this is C1, and this is G1 and P1, G2 P2, G3 P3. This is C1 into P1. This is C1 into P2, and this is C1 into P3. This is C1 into P1 into P3, and this is C1 into P2 into P3, and this is C1 into P1 into P2. So in these, Ci dot Pi is done, as you saw back in the uh, ah, as you can see here, this part is done first, all parallelly here, and after that it's added with the G3 values and G1 value, G2 value, to get the output C2, C3 and C4. So first these all are done parallelly, and then it's added to the GI value, and these all are done parallelly. All of these, this is done first, and then this is done. So the next topic is going to be the advantages of carry look ahead adder, which will be taken by my teammate Sharavana Ragav.
Advantages of carry look ahead adder. Faster computation. CLA carry look ahead adder significantly reduces carry propagation delay by using parallel carry computation. This results in faster addition operation compared to the ripple carry adder. The ability to compare carries in parallel improves the overall speed, especially for wider bit adders like 16, 32, and 64 bit adders. Scalability. CLA is highly scalable, allowing it to handle larger bit widths 16 and 32, etc., with minimum performance degradation. This scalability makes it suitable for use in modern processors and digital systems. Cascading CLAs allows even larger adders to be built while maintaining faster performance. Improved performance in processors. Carry look-ahead adder is widely used in high speed processors, particularly in arithmetic logical unit (ALUs). Faster addition means quick execution of instructions, improving the overall processor speeds for range of operations like arithmetic, logic, and complex computation. Application requiring high throughput, for example, video processing, machine learning, gaming, benefits from CLA speeds improvements. Reduced propagation delay. Unlike a ripple Kelly adder, where delay increases linearly with bit width, CLE propagation delays grows logarithmically. This enables CLA to maintain fast performance as bit width increases, allowing the process to operate at higher clocks frequencies. Disadvantages of carry looker header. Increased complexity. The logic requires to complete, generates, and propagate signals for each bit increases overall complexity of the circuit. This makes the CLA more complicated to design compared to the ripple carry adder. More logical gates. The CLA requires additional logical gates to handle the computation of the carries in the parallel. Each stage of the adder needs an hardware to generate and propagate signals, as well as a carry prediction. This additional hardware increases the overall gate count, which may not ideal for a system where area and hardware efficiency are critical factors. high power consumption due to additional gates or in the logical circuitry. CLA typically consumes more power compared to the simpler adders like triple carry adder. For example, for extra hardware required for parallel carry computation leads to increase in power usage, making CLA less suitable for low power applications. In systems where power efficiency is critical, for example, mobile devices and embedded system, this may be a significant drawback. Complex designed for large bit widths. As bit width increases, maintaining the complexity of the look ahead adder logic becomes more challenging. For example, adder 64 bit 128 bit, the design and the implementation of the CLA becomes unwidely requiring hierarchical CLA structures. Designing and optimizing these largest uh, structures is more demanding process, requiring the sophisticated techniques to manage computation effectively. CLA in modern systems. High speed processes used in ALUs to accelerate arithmetic and logic unit, improving the overall speed of a CPU, especially beneficial in processors for gaming, servers, and high performance computing. Digital signals processors DSP. CLA is used in DSP for real time processing of audio and video and large scale data sets, speeding up operations like fast Fourier transforms and signal filtering, essential for applications like audio systems and video compressions. Graphics processing unit, utilized in GPUs for high speed arithmetic in tasks such as 3D rendering, gaming, and machine learning. CLA helps process large volumes of data in parallel quickly. Embedded system. CLA is found in embedded system like automotive, medical devices, and IoT where real-time processing is crucial. Impact of CLA on performance. Reduced critical path. CLA minimizes the critical path in arithmetic circuits, reducing the delay and enabling faster operations. Higher clock speed with reduced carry delays. Systems can run higher clock speeds, improving the performance in the processors and DSPs. Efficient processing improves the efficiency in tasks like scientific simulation, machine learning, and parallel computing by speeding up the arithmetic operations. Power performance balance. Through CLA uses more power. It is faster operation can help the system to finish tasks quicker, reducing the overall power consumption in high speed systems. Conclusion. Takeaways. CLA improves the speed of addition by reducing the carry propagation delay. It is widely used in high performance systems due to its ability to handle large bit width operations efficiently. However, it comes with trade-offs in terms of complexity and consumption. Future outlooks. CLA is still a relevant digital design and continues to optimize for higher performance. Thank you.